Lecture 8, the periodic table. And when I talk periodic table, I've got a lovely drawing of the periodic table here. I draw this on the board all the time at school. It's decent. It gets the point across, but I would recommend that when I lecture about the periodic table, probably from now for a good while, you would either open a tab of the periodic table on your computer and have it open while I talk, or print one out, find one that's printed out for you to look at. It helps to have one for you to see. You can open the one I sent, open the AP Chem one. It really doesn't matter if the periodic table you are using has elements like 114 to 118 named correctly. They're not going to be very useful to us. They'll be on there. I don't care if you're calling them somethingium or oganesson and fluorovium. It doesn't matter. The part of the periodic table we're mostly concerned with is here, the top part. Remember, Dmitri Mendeleev came up with the concept in the 1800s that the elements could be arranged by chemical properties, and when you did that, they make a periodic table. Why is it periodic? It's not periodical, it's not a newspaper, it doesn't happen every once in a while. Periodic means that the chemical and physical properties repeat in a pattern. A pattern is followed, so group 1 would have stuff in common. Group 2 would have stuff in common. The middle, things in common. And properties change as you move across the periodic table. When we get to chapter 7, periodicity, we'll look at these trends and how they relate to this. Elements are arranged in order by atomic number. Increasing atomic number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, the whole way. If you go across the periodic table, it's a period. Period is horizontal, and group is vertical. You might want to write this down that groups are also called columns, and families. They're called families sometimes. The idea behind calling them a family is that they're a lot alike. But that, for some cases, is like saying, oh, you have to be exactly like your family. Some of the families are exactly alike. And you know families like that. But then some families are nothing alike. If you look at group 14, the top is nonmetals. Then you have metalloids, and then you have metals at the bottom. There are definitely some families like that, too, that are not a thing alike at all. In your packet, I've got 2 systems for numbering the groups. I learned in high school to start at 1 on the left and just count straight across. There's 18 of them, and those are your group numbers. That's the one I use. That's the one my college professors used with the occasional mention of the other group names. Your textbook uses 1A, 2A, and then B for down here. So the periodic table I included in your packet right there has both. More often than not, the ones I provide for you will be numbered 1 through 18. We'll work on that as we go. Dividing periodic table by properties. 3 big ideas. Metals, nonmetals, metalloids. And my drawing's great for this. The metals are found almost all over the periodic table. If you don't know what it is, guess metal. I think 70%, 75% of your elements are metals. Metals are found at the left, the center, and the bottom of the periodic table. There's this zigzag dividing line over here, group 13 and friends, the zigzag dividing line. This side and below are metals. Metals have high density. Metals conduct electricity. Metals are strong. They resist breaking. They're usually shiny. Those are properties they share. Nonmetals are found over here at the right of the periodic table and have the opposite properties from metals. A lot of times they're gases or liquids. They don't conduct electricity. Sometimes, like this nitrogen and oxygen out here, you can't even see them. They're gases. That's great. Lack of common properties, though. Like metals are usually shiny, there's nothing we can say. Coal is mostly carbon. Nitrogen is a gas. Those are examples of nonmetals. Carbon, nitrogen, not a lot alike. Metalloids are found down this zigzag line at the right. There are 6 of them that everybody pretty much agrees on. Boron, silicon, making sure I catch the right ones for these. Germanium, arsenic, antimony, Sb, and tellurium. Those are the ones everybody says. You'll also see polonium, which is down here, and selenium, according to some people. You'll see 6, 7, 8, some combination of that. Most important thing is they divide the metals from the nonmetals and have properties in between. There you go. Dividing the periodic table by groups. These names are important. And if you don't catch them from when I say them, look them up in the texts. Check them out online. Group 1 or 1A, depending on which way you divide the table, which numbering system you use. Alkali metals for group 1. These are super reactive. They're like crazy. You throw them in water and they go boom. Group 2 or 2A, the alkaline earth metals. Notice they've got metals in the name. These are still pretty reactive, but not quite as crazy. Pretty close. 3 through 12 or 1B through 8B is this whole middle section. Those are your transition metals. Transition as in connecting this side to this side, and connecting properties kind of too. You've got a couple stray metals down in here, but the next group, you don't use this one too much. Some people will say the oxygen family. Group 16 is also called the CHALCOGENS, chalcogens. Chalco is chalk. They're chalk formers. Never actually heard anybody call them that. Sorry. Group 17, I definitely hear this one. They're the salt formers, the halogens. Halo, like halide, salt. Halogen means salt former, and they do, like sodium chloride. Chloride's in group 17. Group 18 are the noble gases, not super reactive, full outer shell, if you remember that from regular chem. Good deal. So that's your periodic tables divided by properties with metals, nonmetals, metalloids, and by groups. Now, when we're looking here at compounds, we should be good to check out some big ideas all sort of smashed together. In other words, this is sort of where your textbook put a whole bunch of information that only kind of matches up. So bear with me here. When we talk about compounds, basically we're just looking at 2 or more elements chemically combined. Great. That definition's typed and you're ready to go. Molecular compounds mean that the atoms are sharing electrons. These are non-metals together. Molecular compounds, we're looking non-metals. First of all, you've got diatomic elements when we're talking about non-metals hanging out together. Diatomic elements are elements that exist in nature as 2 atoms bonded together, if not in another compound. So if they're not bonded to something else, they hang out together. 7 of them. Hofbrinkel, or Brinkelhof, depending on how you want to say it. Hofbrinkel, Brinkelhof, whichever. Hydrogen. Oxygen. You might think of O2, like O2 might be something you remember. Fluorine, Hof, bromine, iodine, nitrogen, and chlorine. Those are diatomic elements. So if I'm trying to add like chlorine to something, I won't add Cl if it's by itself. I'll add Cl2, but if it's hanging out with sodium in sodium chloride, it's legit to be NaCl. You don't need to include the 2 if it's in another compound. Molecular compound, more than one type of atom, chemically bonded, where they're sharing electrons. A covalent bond, if you remember that. Who likes to covalent bond? Nonmetals like covalent bonds. So we're looking over here for molecular compounds. And what type of elements? Nonmetals. Big class of these molecular compounds are your organics. Organic compounds contain carbon. I know you hear about organic farming, organic growth. That means more of a natural growth. When we talk about organic chemistry, it has nothing to do with that. All it means is there is carbon in a compound. Easy. A hydrocarbon is an organic compound that contains only exactly what it says. Carbon and hydrogen. Carbon and hydrogen. Alkanes are a specific type of hydrocarbons. If you've taken organic chem, you learned your alkanes, alkenes, alkynes, and if not, when we get into the school year, once we're schooling, someday you'll have an organic chem packet to do. We'll work together on it, get there. There's information in your text, and anybody who's taken the course can help also. I want you guys to have a basic idea of organic nomenclature, but this is just like, here it is. An alkane is a hydrocarbon, so it's just carbon and hydrogen with all single bonds. Carbon's able to double and triple bond, and those are different classes of organics. Alkenes, same thing but with an E, has at least one double bond, and alkynes with a Y have at least one triple bond. That's just FYI, not anything that was in the notes, just letting you know. Formulas for compounds, molecular and empirical. Molecular formulas tell you what atoms actually are present in the molecule. They indicate actual number of atoms. So there's nothing reduced. If I have C2H6, that means I have 2 carbons and 6 hydrogens. Cool. Empirical formula tell me the lowest ratio of subscripts in a compound. So it's a reduced formula. C2H6 as a molecular formula, divide all of it by 2, gives me CH3 as the empirical formula. Are we going to calculate? Yes, we are. Not yet. Right now, I'm just looking at which is which to set you up there. Molecular versus empirical. Should be good there. For ionic compounds, we'll introduce these next time. That's what the notes are all set for. We're good to go. Molecular compounds was it for today. Ionic is pretty easy, and it leads us into ionic formula writing and nomenclature next time as well. So that was Lecture 8. See you for Lecture 9.